So let's keep working on our code for solving the linear regression problem using the mini batch gradient descent method, right? And it's a very general method. In the previous video, we talked about how to construct the graph, right? And in this video, we're going to talk about the code for executing the graph. We're going to talk about the graph execution phase. So to execute a graph, we will need to open a session first with tf dot session as ses. And before we do anything else, we must remember to initialize all the TensorFlow variables first, even though we have just one variable, which is w here. Right? We only have like one variable. But nevertheless, let's still call the global initializer, basically. So global variables initializer. It's a very long name, but it allows us to actually initialize all variables. And now we have to introduce some definitions, some concepts, basically. Right. So the major difference between the mini batch gradient descent and the batch gradient descent is that in the mini batch gradient descent, we only feed the training algorithm a subset of the entire training examples every iteration. But in the batch gradient descent, we feed the training algorithm the entire training dataset at every iteration. So here we are actually using the word iteration to mean one update of the weights in the neural network. So every time we make an update to the weights, that counts as one iteration. And there is another terminology that's kind of used very often in machine learning community, which is the epoch. E-P-O-C-H, epoch. So what exactly does an epoch mean, right? So one epoch means a complete pass through all training examples in the training dataset. So by the end of one epoch, the neural network has been exposed to every training example in the entire training dataset exactly once. And by the end of two epochs, the neural network has been exposed to every example exactly twice. Right? So for batch gradient descent, because every update to the weights or every iteration is computed from all training examples. So one iteration is like equivalent to one epoch. There's no difference. But for the mini batch gradient descent, every update to the weights is actually computed from only a subset of all the training examples. So it takes multiple updates or multiple iterations to actually go through one epoch. And the exact number of iterations it takes to go through one epoch is actually determined by the total number of training examples in the entire dataset, and the number of training examples in the mini batch, which is usually called a batch size, which is also a hyperparameter that you can adjust for your particular dataset, for your particular application, basically. Right? The batch size is used to indicate the number of training examples in one mini batch. So suppose we would like to have like 70 complete passes through the entire training dataset. Then the number of epochs that we would like to sort of train the network is, let's call it n epoch. N epochs, let's use plural, that's 70. So we want to train the network for like 70 epochs, which means that the network must be exposed to every example in the entire training dataset exactly 70 times, right? And then suppose we choose our batch size to be 100. So every mini batch is going to contain exactly 100 training examples. So batch size equals to 100, right? 100 training examples. Then the number of iterations it takes to reach one epoch which is also called the number of batches that's needed in order to reach one epoch, is just the total number of examples in the entire dataset divided by the number of training examples in a mini batch, which is the batch size. So the number of batches, or the number of iterations that we have to sort of that the number of mini batches that we have sort of to iterate through in order to reach one epoch equals to, so n batches equals to the total number of training examples in our entire fake dataset is n row. That's like 10,000, right? So n row divided by batch size. So in Python 3, this division between two integers is going to return a float. The numpy seal function, the numpy seal function will return actually the minimum integer that is larger than or equal to this particular float. And we talked about this. I have another sequence that's called a hands-on start to Python, in which we actually talked about the difference between Python 3 and Python 2. In Python 2, this division between two integers is going to actually give you a integer instead of float. But here in Python 3, it's a float. So you have to do this kind of conversions to convert it into a int, actually. And with all these definitions, we can now write our loops to train the neural network. So we first loop through the epochs. So for epoch in range and epochs. That's just a plain Python for loop, right? And you can sort of, if you don't really know how to write a Python for loop, you can sort of take a look at my hands-on start to Python sequence. It's not completed yet, but at least I have covered the for loops for now in those sequences. And then for batch index in range, the number of batches, right? Number of batches. So it's a nested loop. You have a for loop inside of another for loop. Inside the loop over batch number, the first thing we need to do is to actually retrieve, say, 100 training examples from the entire training dataset, which has actually 10,000 training examples in total, right? So we can encapsulate this kind of a data fetching process inside of a function, and let's call this function fetch batch. So x y batch equals to fetch batch, and it's going to take two inputs. The first one is going to be batch index, that's the iteration index here, right? And then the second one is going to be batch size. We're going to write the body of the function later on, but let's look at the signature of this particular function. So the signature of the function will take two inputs, right? The batch index, which indicates how far along you have been sort of retrieving data from inside of the entire dataset, right? Batch index, and then the batch size. That's for each batch you are retrieving like a 100, right? So if the batch index is like a 2, you are doing the third retrieve, right? So you are going to start with start from the 300th element inside of the entire dataset, right? And then from the 300th element to like 400th element, that's going to be the dataset you have to fetch from the entire dataset and return. And the output, right? We will have like two outputs for the fetch batch function. So the x underscore batch is going to be used to store the input data x1 and x2 together with the bias term x0, right? That's as a non-binary, and then y_batch is going to be used to store the ground truth output that corresponds to the inputs that's inside of the x_underscore batch, right? And all those these two numpy arrays are going to be have a row number that's the batch size, right? So it's 100 for us. And after we have fetched the example data for the mini batch, we can feed them to the training operation, train op. So we define a training op. Using a feed dict. Basically, what we can do is to actually training_op. That's our training operation. It's a node it's an operation node that we constructed. We added during the graph construction phase, right? And then feed dict equals to. So what's going to be our feed dict? X is going to be x_batch, and then y is going to be y_batch, right? And that's don't forget that both x and y were defined as TensorFlow placeholders, so they can accept different initialization values for every iteration. So as we actually run this training op, this operation inside of this nested loop, this x batch and y batch are going to be replaced for every iteration, right? Because this is in the innermost loop, so x batch and y batch are going to be updated, right, for every loop. And by calling sys.run training op with a feed dict, we're basically initializing x and y, these two placeholders that we initialized here. We define here, right? We're initializing these two placeholders with a new batch of input and ground truth data for every iteration of the innermost for loop, right? So by now our loop body is actually pretty much complete. But before we exit the active session, we need to call the eval method on the weight tensor W. So now call the eval, and then we'll have to sort of assign it to a new Python NumPy array. Let's call it best W equals to W eval. And after we actually close the active session, we need to remember to close the log file writer object also. Writer.close. We need to do that. Don't forget to do that. Right. Now we still have two more things that we need to complete. The first thing is that we need to write the fetch batch function. Right. We don't really have this function yet. We need to write it. If you don't know how to actually write a Python function, I will explain that in my hands-on start to Python sequence. Right. But we already know the signature of the function, right? So let's add the function here, because the function is going to have to access ground truth vector and the input data with bias a matrix, the two-dimensional Python NumPy array. So let's add the function here. Let's call it def fetch batch, and then the first index is going to be a batch index, right? And then the second input is a batch size, right? And inside of this function, we will need to access this input data with bias and also the ground truth. So we need to declare them as global. and then ground truth. And the purpose of this function is to return a subset of the entire training dataset, and this subset has a batch size, this many training examples in it. So we need to compute a starting index and an ending index for this subset based upon this batch index, right? So start index, it's called a start index, is going to equal to the batch index that's passed into this function times batch size. That's also passed into this function. And then end index is just going to equal to start index plus batch size. Right. But one thing that we have to be careful about is that we need to guard against the possibility that this end index goes beyond the total number of training examples in the entire training dataset. So if end index is larger than or equal to n row, right? We only have like this kind of 10,000 training examples in our fake dataset. So if the end index actually goes beyond it, right, we need to do something else. We need to guard against that, right? What does it mean, right? When n index is larger than or equal to n row, it means that we have reached the end of one epoch, right? We have gone through the entire dataset. We have gone through, the neural network has looked at every training example in the entire training dataset once, right? So we have reached the end of one epoch. So what we need to do is to actually start a new epoch. Right? But before we can return a mini batch from the new epoch, what we need to do is actually to shuffle all the training examples inside the complete dataset, so that the examples are not in the same order as before. When we talked about mini batch in a previous video, the mini batch gradient descent in a previous previous video, we were sort of saying that the mini batch has to be retrieved as some kind of random subset, right? But here, we actually, for every epoch, we're actually randomly shuffling the entire dataset. So the effect is, if you retrieve the randomly shuffled, if you retrieve from this randomly shuffled completed training dataset in order from top to bottom, it's just like picking random mini batches. Right. But here, instead of just build the randomness into the mini batch retrieving process, we can actually randomly shuffle the entire dataset and then retrieve from this randomly shuffled dataset in a specific order. So in order to do that, in order to sort of randomly shuffle the entire dataset, what we are going to do is the first thing we're going to do is to generate a NumPy array, a range n row. So this NumPy array perm is going to have integers inside of it, and the integer is going to go from 0 to 10,000, right? N row to n row, and then we can randomly shuffle this array basically. So np.random.shuffle perm, and now we can use this randomly shuffled array to index into the entire training dataset. So what we're going to do is we're going to use this perm, this randomly shuffled perm, to rearrange. So input data with bias equals to input data with bias. But now we use perm to rearrange as an index array to rearrange the ordering of all the examples, of all the rows, basically, all the rows inside of the two-dimensional matrix. And then we have to do the same thing for the ground truth vector. And now we can just reset the start index to 0 because it's a new epoch now, and then the end index to batch size, right? The end index to batch size. And now we can actually just retrieve. We can just by the end of this is already the end of the function now. We can just by the end of this function, all we have to do is to actually return the subset by using these two, by using the start index and the end index. So return input data with bias start index colon. So this is a range operator in NumPy. It allows you to actually select a portion of a particular matrix. That's our first output, and then that's our second output. But for the second output, we have to call the reshape -1, -1, 1. We want one column and a number of rows that's kind of computed automatically by NumPy, and then start index to end index. Right. And that's sort of the body of the function. That's sort of the body of the function, and we have pretty much finished writing it. And we have one more thing that we have to do in order to actually finish our code. The last thing that we want to do is to add some information to the log output file. In the previous video, we have defined this MSC and also this MSC underscore summary, right? And this MSC summary actually uses MSC, right? It's supposed to be a tensor with just a scalar tensor with a string as its only element, right? And this string tensor is actually constructed from this scalar, and this scalar is one TensorFlow node. Right? It's obtained from reduce mean, and then the square of error, and then the error is actually sort of computed from that, right? And ypred pred is computed from the matrix vector multiplication between x and w, that kind of thing, right? So what we want to do is we're going to use the MSC underscore summary to actually add information to our log output file. So we're going to do that here. Right. Writing to the log output actually takes some resources. So we don't really want to sort of do this kind of a log output for every iteration of the training process. Otherwise, it's going to slow down our training process significantly. So what we want to do is to write some output to the log output file for every 10th batch index. So what we are going to do is to we're going to do if batch index modulo 10 equals to 0. So at when batch index equal to 0, it's going to write output, and then when batch index equals to 10, this is also true, then it's going to write output, and then so on and so forth, right? So every 10th batch index, right, or every 10th iteration, we're going to write to the log output, right? And then the first thing we have to do is to here MSC underscore summary is actually a tensor, right? It's not really a string. So what we have to do is to evaluate it. We have to call the eval function on it, and then it's going to produce a string for us. Summary, let's call it a summary string equals to MSC summary dot eval, and this dot And this eval method call takes a feed dict as its input. So feed dict equals to x, then x batch, y batch. So the x batch and y batch we're actually using here is exactly the x batch and y batch that we have retrieved from the entire dataset by using the fetch batch function call, and also exactly the same batch that we used to feed into our training op. Right. So the MSE summary, this particular tensor is going to be evaluated for the training data retrieved at that specific mini batch that's used for training the op in this particular iteration, basically. Right. So we also need to know which global step of the entire training process this MSE summary is being evaluated at. And this global step number can be computed from the epoch index, this epoch index, and also the batch index. Right? Let's just call it step. Step equals to its epoch multiply n batches. So for every epoch, we need to sort of do this many batches, right? And then plus batch index, and that's gonna be our global step number, right? And now we can call the add summary method on the file writer object to write this log information to write this information to the log output file. So what we are going to do is to do file underscore writer dot, the method call is called add summary, and then it takes two inputs. One is the summary string that we just sort of obtained from the eval method call, and the second input is the step number, right, that we just computed. And by now we have actually finished coding our execution phase. And if we would like to sort of look at how we can first run this code first. Let's click on run. So now we have finished execution, and let's look at our best W, see if it's close enough to the true W number. Or best W is right here, but I can't see why. Okay, so best W, if I double click on it, it's gonna show me the numbers: 2.5, 1.7, minus 0.8. Right? Is that the same thing as our true value? 2.5, 1.7, minus 0.8. So we have actually recovered the true values, right? And we have a log output this time, right? And it's supposed to be inside of the subdirectory that's called tf underscore logs, right? So what we can do is to actually launch this tensor board. Let me blow up the fonts first. And then tensor board with the log dir given by tf logs. For some reason I am not getting the, oh, I see, it's not on the desktop, it's in my Dropbox folder. Now it's supposed to have tf logs in it. Yes, I have tf logs. So now I can run tensor board with a log dir given by tf underscore logs. Yeah, so now I can open a browser, and then let me just copy over this URL, and then let me just paste it in it. Okay, so now we are seeing our MSE now, right? So this is MSE. How MSE actually evolves through the training steps, right? So the horizontal axis is the step that we computed. Where's the step? Yeah, step that we computed here. And then the y-axis is actually the value of the MSE throughout the iterations. So you can look at how it actually evolves. This button allows you to actually blow up the figure. And if you don't want any smoothing, then you can look at the true evolution history. And um, so that just gives you this. If you click on this war button, it's not the step number anymore. It's actually war time. Right? So some portion of the so that's the scalar, how MSC actually evolves, right? And then if you want to look at the computational graph, it's supposed to give us the computational graph inside of this particular tab, but for some reason it's not doing that. Maybe it's an issue with the browser. Let me switch to Google Chrome, and let me just move this thing over. Okay, so still look at it. Right, the starting value at step 0, it's actually more than 2.4, right? But later on, it reduced to 10 to the minus eighth, 1.4798 multiplied by 10 to the minus eighth, right? And then if we want to look at the graph, that's our computational graph, right? And we can try to make sense out of it, but we're not going to do that today. There are various options for you to actually look at this scalar plot, right? So if I click on the ignore outliers in chart scaling, then some portions of it are going to be chopped off. But if I unclick it, then it's going to display the entire thing. And then if I sort of draw a box on it, it's going to do a blow up view for me to zoom in at a particular section to look at how this thing oscillates. The reason that it actually oscillates is because the learning rate is actually fixed at a constant, right, 0.01. It's not everything, but as we get closer to the optimal value of W, the gradient actually becomes smaller. So the slope actually becomes shallower. It's not as steep as before. So if you fix the learning rate, maybe the step length is too big, right? So you are descending along the negative gradient, right? So but every descent is actually along the negative gradient by a small amount. So you are taking small steps along the negative gradient direction, negative gradient direction. But if your steps are too long, then you may jump into the other side of the valley, right? So that kind of thing will give you this kind of oscillations, right? And these kind of oscillations can be sort of removed by adapting the learning rate to the particular shape of the to the learning process, basically. So as your sort of MSE reduces, you can try to reduce the learning rate accordingly, so that you don't really jump back and forth across the descending valley. And later on, we'll we're gonna look at how to deal with those kind of issues.